to the strong who have made it all the way till almost 4:35 and still are engaged in this conference. Congratulations. I'm happy to welcome you to this session on climate change impacts on water resources and utilities. It is actually the second part of a set of sessions on climate change. I unfortunately could not make it to the prior session chaired by Hammou Laamrani just now. Maybe he can give us some highlights during his intervention, if anything, some key conclusions came out of that. But this we are going to focus on sharing with you 3 expert presentations. One focused on the Jordan Basin, one on the regional level, and then also another on the country level experience related to climate change. So it's really country, basin level, and the regional levels, not necessarily in that order, that we are going to focus on here when we think about climate change impacts, assessment, negotiations, etc. We have, since the agenda has been pushed back a little bit, I'm hoping that if our presenters stick to 15 minute mark or so, we can have at least 1 or 2 questions if possible after each. But if we feel we're going long, we'll hold it to the end so that we give everyone a chance to give. But I'm hoping so that questions remain fresh in your head, some brief Q&A can be after each session. In that light, I'm very pleased to introduce our first speaker, who is going to discuss the impact of climate change on water availability and recharge on aquifers in the Jordan River Basin. And this is presented by Dr. Leah van Wesenbeeck. I got it right. And Dr. Leah is with the management team at the Amsterdam Centre for the World Studies at VO University in Amsterdam. She works on on economic modeling based on climate change assessments and outputs, and how that affects various sectors that we are going to hear about now. She's also been involved not only in work in the region, but also in Africa and Asia. Mozambique and Indonesia are listed here. I'm sure there are others, and as well as held some advisory support on Africa, Climate Africa. There's also Climate Med that maybe some of you have heard about, that provides also assistance thanks to support of the EU on climate and modeling and indicator outputs. She's also a member of the Science Foundation of the Netherlands and a member of the monitoring table on food security. So with that, I'm happy to invite Dr. Leah to the floor so that we can hear her findings about the various sectors associated with her assessment and the university's assessment on the Jordan River Basin. Please.
Okay, so I will try indeed to be within the 15 minutes. Wonderful. So I'm going to present work that has been done in the context of a SIDA-funded project where we had a large consortium working with Juds University, with Al-Quds University, with AXAT as regional partner, and with the American University in Beirut. And this particular work is joint work from our center, the Center for World Food Studies at VU University Amsterdam, together with 2 professors from JUST. So I'm going to say something about what the problem actually is, and what the basic problem is it's twofold. One, you have to understand what, or to predict to your best abilities, what the impact of climate change will be in terms of rainfall. We only focus here on rainfall, I have to say, not on temperature changes. Second thing is, okay, that's rainfall. What is interesting is to see what the impact is of changing rainfall patterns on agricultural revenues, on recharge of aquifers, on the availability of water in the Jordan River Basin, because this is the focus, the geographical focus of the research. So I'll tell you something about how we predicted the rainfall. I will also tell you something, not very technical, about the model that we have developed for the river basin and that we used, amongst others, to predict the impact of climate change. Tomorrow and the day after tomorrow, there will be different presentations by myself and my colleague about other, applications of this model. So, well, everyone knows climate change is likely to affect large parts of the globe, including the GRB. And the region, of course, already faces many challenges. It's not it's very obvious by the title of this conference, it's a fragile environment already. So very important questions for policymakers are, how will climate change affect the region, and where are hotspots, and how will climate change in one part of the region will affect also downstream areas? What will it mean for agriculture, for food production? What will it mean for human consumption? And very importantly, what will it mean for the sustainability of the use and hence the availability of water resources in the region? So how do we start it? Well, you all know there is this big panel, the IPCC, and they have made a lot of global circulation models. They are used to predict the impact of climate change. But the problem is they are on extremely large scale. So they have blocks, let's say, they divide the world in blocks of about 100 to 500 square kilometers, which is huge. So when you want to say anything about spatially specific patterns, you have to take those results and somehow make them applicable on a smaller scale, which is called downscaling. And you have different techniques. You have statistical and process. I will not bore you with that. But the idea is that you use available information from the ground and from other resources to find linkages, to estimate relations between the big things and the very variety of circumstances on the ground. And that's what's been done by our colleagues at JUST for the Yarmouk. So a specific part of the river basin, and they did this downscaling. There is a problem with these huge models, that they have a variety of outcomes. That if you take their potential impact, they vary greatly. So also even on this large scale, when you look at, say, the next century, then we have like horrific scenarios and we have kind of okay scenarios. So when you downscale, of course, you add up to this uncertainty. Nevertheless, you have to do something. So we took more or less the average, so the median of these predictions, and downscaled them to the Yarmouk River. And then, second step, we used this downscaled predictions for the Yarmouk and extrapolated that results to the river basin. So how do you do that? Well, we have a big basin. For a small part, we pretend to know what the rainfall patterns will be. And the question is, when we look at rainfall patterns in the past, can we say something about how these rainfall patterns and the rainfall patterns in the areas where we don't have predictions, how they go together? Can we estimate the relations between those different rainfall patterns? And we did this by using historical data going back to the 1980s and saying, okay, how can we relate those data? So what came out is that we said, well, there is kind of a south-north gradient in rainfall patterns. And that's how we did a very simple thing. We can improve upon it in next steps, in next versions of this model. But what we did is have a linear relation with a north-south gradient. And what we came up with is then that we have a scenario specification for rainfall. So these are the areas included in the river basin. So when we mention countries, it's not the whole country, it's only the part of the country in the basin. So Israel has only a small part, Jordan, so the same holds for every country. Some countries have large parts in the GAB, most of them only small parts. So what you can see is that this is the prediction for the year 2050. That it is predicted that for the GRB as a whole, there will be 600 million cubic meters less rainfall annually. How is it spread over? Because that's one thing. Okay, that's a large number, but it doesn't tell you that much. What you probably need to know is that the rainfall currently is about 6,000 million cubic meters. So it will mean that on the whole, there will be a decrease of about 10%. Doesn't tell you anything yet, because what you need to know is if there are hotspots where the rainfall really dramatically is reduced, or if it's more or less distributed evenly over the region. Well, as the map shows, there are regions, in Syria particularly, where rainfall even is projected to increase. And there are regions, the deep red ones, where rainfall will decrease very much. And you see the oranges and the yellow shades in between. So we're having this spatial pattern of daily rainfall. I have to say it's not only spatial, it's also daily. Then you can find out, okay, what does it mean for agriculture, for example? And therefore I have to take you one step back and tell you what type of model we actually used. So I told you this already. So the model is very, very detailed. Not so much spatially. We have 48 districts covering the whole of the GRB. We have 26 two-weekly time steps. So the rainfall, the daily rainfall, is aggregated to 2 weekly time steps. And we have 4 layers. What do I mean with layers? We have, in the GRB, most of the surface flows are controlled flows. So we have one layer which is controlled surface flows. We have one other layer which is natural surface flows. So that makes 2. Then we have the root zone, where the plants take their water. Then we have the aquifers, so that's 4. And we have the rivers, which is 5. Why do we distinguish all these layers? Because the interconnectedness in the GRB is tremendous. So what happens in surface water, it percolates, it evaporates, it's runoffs, it's used by the plants. So there are lots of processes going on. And to capture them in sufficient detail, we are using this 5-layer construction. Then there's another very important challenge for the region, that is the quality of water. So in the model we have pure water, just as a kind of a category. We also have water which is salinated. We have water that is polluted by nitrate, and we distinguish water that is biologically contaminated. And we have like 4 streams going separately. I will go a bit, but so we have 4 streams going separately. But of course you cannot choose, the plant cannot choose, and I cannot choose just to take pure water. So while we maintain mass balances, at the same time we require that the user is forced to take whatever he gets. So if the consumer is linked to a public water distribution, then the quality of water may be very good. But if I'm a plant and I'm just sitting somewhere, then I have to use whatever water is available. Go back one part to just show you how the interconnectedness is really working. This is just showing how complex things are. I can make a more complex picture, it looks more impressive perhaps, but this is already, for me as a simple economist, complex enough. So how do we go from water to agriculture? Well, I told you the plant just has to take up whatever it has. And it means that if, let's say, the rainfall increases, or something changes water availability, there are 2 types of agriculture that will respond. One is the rain-fed agriculture, where if there's more water, probably the farmers will not increase their area, but plants will have more water and they will grow. They have a yield response. But if the water is very salinated, there will be a bad response also of yield. And if it's contaminated with biological, then the plant will not suffer, but the people who may eat it may suffer. If you look at irrigated lands, if there's more water available, then probably, because the yields, that depends on how efficient irrigation is, then probably there will be an increase in irrigated area. Not so much to a yield response directly, but an increase in irrigated area. Is the irrigated area the same? No, because we assume, as is usually done, that the best areas is taken into production first. So we have a map that says, okay, these are areas very suited, less suited, least suited. So whenever increased water is available, increased amounts of water are available, the response of irrigated area will not be a 1-to-1. So this is just giving you some idea, some intuition about how we model the response of agriculture. Going with giant leaps towards the consequences, there is an interesting thing, because you would more or less expect perhaps that if you have a decrease of 600 million cubic meters, that it would be a 1-to-1 response to agriculture. And there isn't. And the reason why this response is different is because the system responds. The system responds because of these very complex hydrological relations. So what happens if there's less water falling, there's less runoff to the rivers. So you see it here, it's 160 million cubic meters less that is going into the rivers and is not used for agriculture. So that means that out of the 600, 160 is already cushioned by not flowing into the rivers. There's also less extraction. So when there's less water in the rivers, people also extract less. So there's a kind of a behavioral response that takes up, again, something like, not so much, but again, 80 million cubic meters. And then there is groundwater. That was one of the elements in the title. What are the consequences for the groundwater reserves? If there's less water falling, there's less water percolating, there's less water reaching the aquifers. So the groundwater stock changes are affected negatively. You can see I don't have the maps here presented, but if you look at least for the countries, you can see there are very different responses on groundwater. And for the GRB as a whole, it's about 160 million cubic meters. That is less. So this is comparing the baseline with this climate change scenario. So compared to the baseline, there will be 106 million cubic meters less as recharge in groundwater in the whole GRB. Given that already sustainability is very much questionable, this is of course a very serious point. This is all assuming unchanged policies, unchanged technologies, because we don't know what will become available for, say, increasing irrigation efficiencies, reducing the huge amount of leakages. So this is all on the unchanged technologies and behavior in terms of policies. So what does it mean for household demands? Another important factor. So for you on the left-hand side, you see a picture of what is now the household demand, or the household use, I should say, in liters per capita per day. So the darker blue, the higher the availability or the use of water for human consumption. And if you look at the picture that is yellow, from yellow to red, you can see that there is a negative impact, but that it's not so bad. I mean, the worst impact is only 3 liters per capita per day. And this is really the consequence of all the systemic responses that cushion all the way, they cushion every step of the way until the final one is the consumer. And he is not really that much hit. Who is hit? Well, agriculture. So the consumer may not be hit by direct response on water, but he will be hit because of a reduced ability to produce food, because that's one of the main things. So here we express it in revenues to be able to more or less add different types of crops. And what you see is only in Syria, because there we have more water. There we have an increase in agricultural revenues of somewhat like 15%. All the other parts of the GRB will lose significantly. And it's more than 10%. So that would be in the area of, let's say, 100 million Jordan dinars. That is about 10%, 12% of the current agricultural revenue. So it's a lot of money. And also a lot of cereals and a lot of other crops. So it's also impacting on food security. So I'll tell you a bit about this initial shock and system response, because that's very interesting. Because that's what sets this apart from local analyses that just say how much rainfall we're going to expect and what are the local impacts. Because a system response is also that it rains there and something happens there. So what you see is there is a huge system response. That's the green bars. And it's taking away almost 500 of the 600 million cubic meters. And if you look at this picture in the bottom, you see what is reacting the most. So it's usually the purple bar, which is evaporation on non-agricultural land. So it's the direct evaporation of land. And that is reduced very much. And then there are other elements, and they vary more or less between the different parts of the GRB. So the system cushions. It will also cushion increases, by the way, because it works two ways. So if you increase in rainfall, it will also not lead to an increase in agricultural revenues. So you have to be careful when you analyze what's happening, that you take into account this type of hydrological responses of the whole entire system, upstream and downstream, and locally going down in these layers. So I will end to give you some time to ask some questions, which I no doubt you will have, is that yes, it is a major shock, 10% of the less rainfall compared to now. It's partly compensated by reduced evaporation, 300 MCM. We saw all the other parts also. River flow substantially lower. Not so much immediate effects on human demand for water, but yes, there is a problem with food security. And the recharge is very negatively impacted, which means that there's serious doubts about sustainability of water resources under climate change. Thank you very much.
Thank you very much. I'll invite you to stay there in case there's a slide to show. So, and rather than taking questions there, if you don't mind standing.
I feel very comfortable.
Because I'm sure there might be someone who inquires on a slide. I'd like to open it up to the floor. Any inquiries? Because I have a lot of questions. But any inquiries from the floor? Questions for clarification? Please. And please introduce yourself. And there's a mic if you could.
John Wilson, USAID. One of the projects we're now involved in is looking at aquifer recharge, and you're